Good afternoon, Professor.
Good afternoon.
I have a question in the homework. Couple.
Sir, do you want to share your screen?
Yep, I can share my screen. Just it will be this one.
Sure.
For question 2, I'm really confused on how to solve it when we short circuit it with the 1 amp.
The 1 amp will get open circuited.
No, I mean like for the 5 volts, so we short circuit the 1 amp.
All right, so you want to know what happens? So what's going to happen to the 12 ohm resistor?
Do we disregard it? Because
Yeah, so I mean, disregard basically if you have basically there's just a wire, there's just a short circuit in parallel with the 12 ohm resistor, right?
yes.
And then that means that the current, any current will avoid the 12 ohm resistor and will flow through the wire, the short circuit. Does that make sense? So any current that goes into the spot that you're pointing it will not flow down there. It will all go around. It will go through the short circuited battery. If you go left, no, it will go like, so if you redraw, okay, hold on, let me just, I think it will let me draw over this, or maybe not. Hold on, let's see if it'll let me draw. I mean, basically just draw a short circuit in parallel with the 12 ohms, right? So yeah, exactly. So just short circuit the battery. Okay, so what I'm trying to say is that maybe I'm saying too much. Yeah, so that's going to be a short. So just replace it with a wire. Yeah. So you can effectively short circuit the 12 ohm, is what I'm saying.
So at this node,
right? Right. Yep. Yep.
So at this node, it's gonna also measure 5 volts.
Oh, wait a second. You're talking about, sorry, I thought we were talking about disconnecting the battery.
No.
You want to disconnect the current.
Yes.
Okay. So you cannot get rid of the 12 ohm resistor in this case.
Yeah, because I was.
Yeah. Right. And so I would redraw this circuit. Let me just see. Actually, let's see. Yeah, so I'm trying to think of how I can give you a hint without giving you the answer, without telling you how to solve it. One of the problems I have is how to help people without solving the problem.
I mean,
so
do we because for one, I did the method that I actually added the in series resistors and I used voltage division, or in parallel, and I used voltage division. Yes, it's a thinning line.
Oh, we got some audio.
Yeah,
you got some musical accompaniment.
Singing.
Props to
Looking
that.
at a Justin Bieber.
You're no Justin Bieber, sir. I'm sorry. Can't hit the high notes like Justin. But I would love it. I would love it if you just randomly threw out more of those musical excerpts for us during the lecture. Okay, let me see if I can help you without solving it. Um,
Because I
okay.
was thinking of
So the problem with voltage division, right? I, first of all, it's not a bad idea. It's just that you got to keep in mind that um, the voltage division is when you go from a voltage to back to ground. But here, you're not going back down to ground, right? So I think the way I would do this,
KVL.
hold on, there's probably an easy way to do this here. Hold on. Yeah,
You can
so
combine the 15 and the 25, correct?
you can combine, I mean, yeah, you can definitely combine the 15 and the
And then
25.
do a nodal analysis, I'm assuming.
You can just, hold on. So the 45, the 15, and the 25 are all in series. Um, hold on. And so there, you don't want to, oh, we're missing something really basic here. So, yeah, this is actually a good question. I like this one. Makes you think.
I don't like it.
No, I mean it's good. It's good to think about it. I mean, you can figure out okay, I think I got it. You can figure out how much current is flowing down the 12 ohm resistor, right? Hope you can see
Yes,
that. Right.
because
And
anyway,
so
these are in parallel, so it's the same voltage here, and we have resistance, so we can find current.
I'm just saying down to 12 in your little picture, you can figure out how much current is flowing down the 12 ohm resistor, correct?
Yes.
So you can also, for this circuit, you have a battery that's connected to a network of resistors. Um, and so the way you should think about it is the following. For current to go from the positive end of the 5-volt battery back to the negative end, what are the possible paths that it can take? Oh, you know what? Hold on a second. Yeah, I told you, my intuition was right. We're missing something major. Um, I think I almost got it. Let me just double check. So think about you're a positively charged particle. You come out of the battery pumps you out of there. You go up and then you make a right turn. You're heading towards the big blue dot, right? Your job is to get back to the negative terminal of your battery, because that's what a battery does, is it sends positively charged particles across, through the circuit. Yeah, there you go. So the question is, when you get to that blue dot, what are you going to do? What are you going to do? I really like this problem.
I have
Are you
two
go?
ways.
Yeah,
I can go left, or can I go right, or I can go like forward, straight.
yeah.
Three ways, not two. Three
The
ways.
thing is, notice that the yeah. So notice that those three resistors, the 45, the 15, and the 25, they're connecting a node to they're connecting a node to itself in a way, right?
Yes, they are.
Right. And that's the confusing part. And so the question is, when a positively charged particle gets to that big blue dot, where will it go? Will any of it go up, or will it all go straight down? Actually, I'm going to leave it at that because I think I've already given you a lot to work with. So the way to think about this problem is, think about, there's probably a way to redraw this that this will become really obvious. If you redraw the nodes of this circuit.
That's the thing. How do you redraw this type of circuit without making, like, with still keeping the 12 resistor, 12 ohm resistor in parallel with the 5 volt, and the same thing, the three resistors maintain still the node 1? Like, it's just confusing. Like, I was trying to
Yeah.
draw it, but it's not the easy.
Yeah, so there's a question on the chat, and the question is, so it won't go up because there isn't a way in which the resistors above reach ground. It's more that if it were to go up, right? If it were to go up, it would have to end up at the same spot, right? So it would incur resistance to get back to where it was. Which should make you realize something. Let me think. There must be. Let me just look at it for another minute.
Yeah.
Yeah. So current takes the path lead, but you should be able to formulate it in terms of. See if I can draw quickly on my pad here. Yeah, it's the homework problems are meant to challenge you. At least some of them.
Oh, they are.
Okay. Well, that's good. When did I postpone the due date of this assignment, right? Or no?
It's due today.
It's due today.
That's why we're all stressing about it.
All right, hold on. See if I can work this out. This isn't gonna make for great video, but
If you want to share your screen, Professor, I can stop sharing mine.
no, you're okay. I'm just gonna work this out, and then if I work it out, then
هو انت اول ما حد يكلمك تجري على طول كده، هو انت مش قلت لي هنزل معاك الحاجات دي وهنزل لك الحاجات دي؟ انت فاهم؟ ما انت متفق معايا ولا انا مش مهم؟
okay. So yeah, you can turn off your screen sharing. I'll try to redraw this.
Okay.
See if I can find the homework. So the new rule is you don't have to mute yourself, but if you remain unmuted, you have to sing. or someone in your house has to sing. This is homework 3, right?
Yes, Professor.
Okay.
Question 2.
Great. All right. All right. So what I would do here is I would redraw this as follows. So basically, I'm gonna work with this node here, and I'm gonna just draw it a little bit differently. This is 5, 15, 12. And this here, this is just the open circuited. Okay. So any current that gets to this point, right? So you have these 3 resistors are in parallel with this connection here, right? Because you can go, this here is basically this here, right? And so all I've done is I've pushed this edge over here to highlight the fact that that the 3 resistors here are in parallel with a short circuit. So any current that enters here, and as usual, I've given away the answer, or I've given away the key part of the answer. So there you go. I'm not a very effective teacher, but so any current that exits here, right? It's going to have a choice of going this way or going this way, right? And I think you can deduce now what it's going to do. And so but actually what's nice is that you have to find the voltage here, right? So knowing that, you still have to figure out what is the voltage at this point, which is still requires some thinking. All right. Let me just clear that. Okay, any other questions about the homework? This is an opportunity to ask those because I'm at work and don't have a mic. All right, Ahmed, are you trying to say something? Is it you wish you had a mic? You want to sing for us? No, totally. Okay. I'm sorry. I would recommend bringing a mic to the midterm. No, actually, probably that would be the only one lecture where you're not allowed to sing. I told you in my I think it was my second year of teaching this course, I had a guy on the final exam not just fall asleep, he also started snoring loudly. And so I had to walk over, had to wake him up. I had to tell him, listen, your snoring is disruptive to the class. Yeah, just another tidbit of information that has nothing to do with the course. Can you explain question 5? It's really confusing. You're trying to get me to give you the answer again. Okay. So if you think about Norton's theorem, right? It's the whole idea of it is that you replace a circuit with a simpler circuit that consists of, so in this box, you're going to have a current source. Actually, let me, here. Let me draw it accurately. You're going to have you get the picture. This is going to be our IN. Right? So you have to draw a circuit that would produce a voltage. Again, I like this question, which means you probably don't. Sadly, that's usually the pattern. So you have to come up with a circuit. So remember, it says draw a Norton equivalent circuit that could represent the unknown circuit, right? So you have to use your imagination and you have to try to come up with a value for IN and a value of Rn that would lead a voltage of 3.8 volts being measured across a 50 ohm load. And that's all I'm going to say for this one, but I'm happy to take more questions.
Professor, can you explain how you get the VEQ at question 4?
Sure, let me slide up to question 4. Let me just. Okay. Okay, so well, the rules are that you want to disconnect all the independent sources, right? And so you will you'll short circuit the battery, you'll cut the circuit here. So this is open circuited, short circuit this, and you'll cut the circuit here. So this doesn't exist, right? This branch doesn't exist. This branch doesn't exist. And what you're left with is a bunch of resistors, just a network of resistors. So again, you have to, starting from point A, to go from point A to point B, how much resistance do you encounter?
Yeah, actually my question was about voltage of VEQ.
Oh, sorry, I thought you were asking for REQ. Okay. Well, you have to ultimately you have to, let's say you ground this, right? Actually, let me just undo all that. So now everything's back in the circuit and you have to find, you're gonna ground this node. And you're gonna have to figure out the voltage here. You're gonna have to find VAB. Yeah, so let's label the nodes in the circuit. Let's call all of this, let's call this node 1. Let's call all of this node 2. Oh, I like this one a lot. I hope this one's not too diabolical. Is there any other non-reference nodes where you have this node, this node, this node? Oh yeah, there's a lot of nodes here. This node. Let's see. So you can label the nodes. I mean, I would probably start by see, how would I start this? The current sources really help you, right? Because you know that here you have the 21 milliamps. And here you have, the 15 milliamps.
Are you saying all of those voltage sources are going to be super node?
Let me just see the question here. I don't know right now which way. Hold on. Yeah, you can absolutely use mesh for this. Yeah, you can use mesh. I'm probably doing mesh analysis when I'm looking at this. Mesh analysis would be the easier way to do this.
What about the node A? Wouldn't be another node here?
Yes, it would be a node. This would also be a node. Hold on. I'm pretty sure that it wouldn't be, you have a certain amount of current flowing in here. You have a certain amount of current flowing here. And then these are all sitting at the same potential. But let me go back. Yeah, superposition would be a good idea as well. Perhaps. Yeah, superposition here may actually be really helpful because then you're dealing with a much simpler circuit in each case. But if you just do mesh analysis, the reason a mesh analysis may be good here is because the voltage, like for example, if you draw the meshes, right? This is mesh 1, mesh 2, say, mesh 3, and then you have that. I think that would be the easiest way to do it. I think that covers everything.
Professor, I have a question.
Go ahead.
Can't you source transform the resistors and the voltage and then combine them with the 15 and then do like a mesh? So you don't have to do I don't know, 4 meshes, 4 or 5? Because that's what I did.
Yeah, I mean, that's definitely, let me just try to visualize that. I think that's a great idea. Again, these are all great ideas. Superposition is a good idea. Also, source transforming. Yeah, I think source transformation is a great idea, because then you're going to have a massive parallel circuit where you can combine a lot of things. So yeah, I think source transformation. Yeah, those are all good ways. At the end of the day, you can do this with either nodal analysis, which is probably the most tedious way of approaching it. You can do it with mesh analysis, superposition, source transformation. Yeah, those are all good suggestions. So hopefully to the original question, hopefully you have some more insight into how to go about solving for VEQ. You know, if you have access, like if you just brute force those 4 meshes, right? And it's actually really 5. You're gonna have 5 independent variables, but you could just, as long as you write out the KVL equations, you can just plug them into a scientific calculator. But the most elegant way is definitely to simplify the circuit with source transformation. All right. Any other questions? Yes, source transformation is great. Thank you. Okay, no, you're welcome. This is one of those awkward lectures where we have a midterm next class. I know you guys are all thinking about the midterm, but we do have to, or I have to, proceed with the course material. Let me just see how many days we have left in the course before, stop sharing for just a second, after the midterm. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, at least 9. Let me see what's the last day of the semester this year. It's usually mid-May, but it varies every year. 5/17. 5/17. So let me now count out how many classes we have left. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 classes left, 10 lectures after the midterm. And we need to get through 4 more lectures. It's doable. Not going to be the easiest thing in the world, but it's certainly doable. Okay. I'm going to start in on lecture 7, which is first order circuits. Lecture 7 and 8 are the least fun for me to teach. But, oh, let me undo that. Or maybe I can do it. Do you guys see my PowerPoint when I do this?
Yes, Professor.
Okay, great. And do you see the presenter view or do you see just the PowerPoint slide?
I see just the PowerPoints.
Okay, great. Yes, I'm not, for me, it's showing the presenter view. And so I'm doing, but I guess Zoom figures out that, that you should not see everything that I see. Okay, so first of all, what is a first order circuit? Basically what it is a circuit with usually one capacitor or one inductor, or it's a circuit with multiple capacitors that can be combined into a single capacitor, or multiple inductors that could be combined to a single inductor. So it's a circuit that has a combination of resistors, capacitors, or resistors, inductors. A lot of text here doesn't work great, but basically we're going to be looking at RC circuits, which are circuits that have resistors and capacitors, and RL circuits. These are used in signal processing, communications. They're essentially filters. So what is a filter? A filter is just, it's a device that selects certain frequencies of excitation. So for example, let's say you want to build a circuit that listens to a particular frequency of transmission. And then if the sender is aware of that, they can emit an electromagnetic signal that, you know, travels over long distances, gets to your little circuit that is able to listen to that frequency and receive it and play back the message. So they're very useful for frequency selectivity. You know, the basic tools of analysis that we will use in this lecture are the same as always. So Kirchhoff's current law and Kirchhoff's voltage law. And you're gonna get this, there's gonna be some very easy differential equations here. The good news is that there really isn't, like, we're not gonna be doing anything sophisticated when solving those differential equations. We're gonna take the really simple approach where you assume a general form for the solution, and then you just plug in your initial conditions and solve for the coefficients. And so you don't have to be strong at calculus or anything like that, or strong at differential equations to do well on this part of the course. And they're called first order circuits because the solutions for the voltages and the currents that we'll be looking at lead to first order differential equations. So something like the voltage of V is equal to VT plus K or something like that. So like very, very straightforward. So first order equations in that they'll only have a first derivative in it. They won't have any second derivatives. All right. So first of all, an RC circuit by itself will not do anything. It needs some sort of initial excitation. And there are two ways. Like one is just in, you know, by we have storage elements. So if there's already energy stored in the capacitor or the inductor, and then that energy is suddenly released to the circuit, that's one way. So a source-free circuit is where you do not have any battery or current source connected to it, but you're told that your capacitor is starting out holding a charge, or your inductor is starting out with some amount of current. So that will be your initial condition. And these source-free circuits may have dependent sources in them. The second kind of first order circuit is one that has an independent source. So it's a circuit that has a battery or a current source connected to it at all times. In this lecture, all our sources are going to be DC sources. So later in the course, in lectures 9 and 10, we will consider RC and RL circuits that are energized by sinusoids. So your actual source signal is sinusoidal. So here we're just going to be looking at a battery that turns on and stays on, or a current source that turns on and stays on. In other words, the voltages of our batteries are going to be fixed. and the currents emitted by our current source are going to be fixed. All right. The source-free RC circuit. So this is the most fundamental first order circuit that you can imagine. So what's interesting is about this picture is that as drawn, the capacitor and the resistor are, I mean, they're really drawn as being in parallel, right? Because they have the same voltage, but they can also be thought of as being in series, right? Because any current that flows around this loop is going to be shared by the resistor and the capacitor. But this drawing here, where the voltage V is defined between the junction between the capacitor and the resistor and ground, is useful for solving for the capacitor voltage. So in RC circuits, the quantity that we're going to be solving for is the capacitor voltage as a function of time. And so whenever you encounter an RC circuit, the first thing that you'll want to do is come up with an expression for V of C. And once you have an expression, and that's going to lead you to your differential equation. And once you solve that differential equation and you have V of C, then you can go about solving for example, IR or V or the resistor voltage. Okay, so what this picture really means is that at some point, this node here was connected to a battery. And then it gets suddenly disconnected. So you're looking to see what happens when this voltage here is suddenly removed. So this circuit has been sitting at a voltage of, let's say, 5 volts. And all of a sudden that 5-volt battery that was connected in parallel to the R and the C. So let me see if it will let me draw on top of this. Okay, so the picture here that you should be, if you have, so you have some battery here, say capital V, that has been connecting and charging up this capacitor. And at all of a sudden, and it's usually at time 0, we cut off this connection. We disconnect the battery. And we're interested in what happens to this voltage, to the voltage across the capacitor. And so usually the kind of behavior that you'll see is that your capacitor starts out at big V and it discharges down to 0. And the key question is how fast, this is time here, right? The key question is how fast does it discharge down to 0? That's what we're looking to identify. Okay, so the energy that has been stored in the capacitor is all of a sudden released to the resistor, right? So the energy has been stored in the capacitor has been charged and it starts discharging. And what that means is that a current begins to flow transiently. And that current will create a transient voltage across the resistor. So again, we are interested in determining the value of V as a function of time. All right, so V started out with some initial value. Let's call that V naught. And we are interested in what happens to that voltage as time moves forward. So the way that this is normally taught in high school is that the capacitor, or maybe first year physics, I don't know, the capacitor is charged up and all of a sudden it starts discharging. So in this class, we think of it as the capacitor has been storing energy in the form of a voltage because it's connected to an external source. And all of a sudden, that external source is removed. And the energy that was stored in the capacitor is now released to the rest of the circuit. So in this case, the circuit is very simple. It's just a capacitor with a resistor. But in many cases, you can have more sophisticated circuits, and we'll look at, we'll look at more sophisticated circuits in this lecture. Okay, and the initial value of the energy stored in this capacitor is equal to 1/2 CV naught squared. All right. So let's apply KCL at this node here. Pretty straightforward. We know that the sum of IC and IR has to equal to 0. In other words, IC is equal to negative IR. That's one way of looking at it. We also know that IC is equal to C times the derivative of V, and IR is equal to V over R. Right? And so let's plug in this expression into here, and this expression into here. Right, so you get a really nice first order differential equation, namely C times the derivative of V plus V over R is equal to 0. And if we multiply, if we divide both sides of the equation by C, you have the derivative of V plus V over a constant, the RC constant, is equal to 0. And let's rearrange this equation. So let's move over, let's separate the differentials. So let's separate a small change in the voltage from a small change in time. And now what we can do is we can integrate both sides of this equation. And so we know that the integral of 1 over V is natural log of V. And the integral of a constant is a linear function plus an integration constant, which can be written as a logarithm. So it's legitimate to write a constant as a log of another constant. Why? Because this log can be positive or negative. So it can represent any constant, positive or negative. Okay, so hopefully you followed this far. Again, if you're unclear as to any of this development, just please let me know, shout it out. And so now what we're going to do is we're going to basically combine the two logs. Remember that the difference of logs is equal to the log of the quotient. Okay, so we have the log of V over A is equal to negative T over RC. And now let's exponentiate both sides. So e to the power of a natural log is equal to whatever the argument of the log is, right? So if e to the power of this is equal to e to the power of this, which gives us this really nice expression, which is that the voltage across the capacitor is equal to a constant A times e to the minus T over RC. And the last thing that we need here is we need to know the value of A. And that's actually straightforward because if you plug in a 0 for T, what you get is that at time 0, we know that our initial voltage was V naught, where we know the value of V naught. So you can think of V naught as a known constant. It was the value of the capacitor right before that battery was disconnected. which means that A has to equal to V naught, which means that the voltage is equal to V naught times e to the minus t over RC. Okay, so before I move on, I just want to give you some intuition as to what this means. What is the largest value that this term can take? E to the minus t over RC. For positive time. For non-negative time, I should say. Right, because we're starting out at time 0. That's our assumption.
1.
That's right. The largest value that it can take is 1. And so the voltage can be no bigger than its initial value. And what happens to this term as time goes to infinity? And what happens to this exponential as t goes to infinity?
0.
It goes to 0, exactly. So in other words, our capacitor voltage, V, starts out at V naught and decays down to 0. So the picture that you see is really here. Your capacitor starts out fully charged with a voltage of V naught, and then it starts decaying exponentially, and it makes its way down to T. So one of the important things is that when T is equal to, when T is equal to RC, then this becomes V naught times e to the negative 1. And e to the negative 1 is about 0.368. So I think E is something like 2.71. So 1 over 2.7 is about 0.368. So when time is equal to R times C, your voltage has decayed down to 37% of its voltage, of its initial voltage. Okay, so the voltage response of our RC circuit is an exponential decay. Right? And that response is due to the initial energy that was stored in the capacitor. And this decay here is called the natural response of the circuit.
Professor, I have a question.
Give me a second, I just have to sneeze.
Yeah, sure.
It didn't come. False start. Go ahead with your question.
Can you go back one slide, please?
Sure.
You did plus LNA because of what exactly?
Yeah, it's a good question. So I didn't have to write it like this, right? I could have written this as, like, normally you would write this as K, just a constant.
Yeah.
Right. But then I wouldn't be able to do this. Right. Okay. So the idea is that you can, so let's say that no matter what your value of K is, sorry, big K here. No matter what your constant is, it can always be written as a logarithm of another number.
Okay, makes sense.
It's just a trick. Yeah, it's just a trick.
Of a constant, basically.
Yeah, it's just a constant. This is just another way of writing a constant. In other words, a constant can be equally represented as the log of another constant. That's all it's saying.
Makes sense.
Yeah. All right. So this time. Okay. So this is called here the natural response, this decay from the initial value down to 0. So at time equals 0, we're starting off with our initial condition. And as time increases, the voltage goes to 0. So in other words, the capacitor starts out fully charged at V naught, And as it discharges, the capacitor's voltage goes to 0. And the time constant is called, so the product of R and C is called the time constant of that circuit. So the definition of a time constant is the amount of time required for the response to decay to 37% of its initial value. So another, this is something that I thought was useful, this notion of, let me see. This is in the slides, but something that's very related. So in medicine, we have this note that they have to, I'm not a doctor as such, I shouldn't refer to myself as one. We have this notion of a half-life, right? So what is a half-life? It's the amount of time, I'm sure you know this, required for a drug to decay to half its concentration. And so you can write a half-life as, let's say, what should we use as concentration? I don't want to use C. Let's, I don't know, X. X of T, right? So if you think about the concentration of a drug in your body, it is often written as an exponential decay. Okay. And so a half-life is the value of T at which xt over x0 is equal to a half. Okay. So in this case, the half-life is when 1/2 is equal to e to the negative t over tau. And again, you can take the log of each side. So you can take negative t over tau is equal to the natural log of a half. So your half-life will be equal to tau times ln of a half with a negative sign. So your t will be equal to negative tau ln of a half. And this is actually how it's generally estimated, is with this. And you need to know what the constant, the time constant is. And so this is very related to RC circuits. It's the same math, except that here, the time constant is given by the product of the resistor and the capacitor. All right. Sorry. See, I think it was a chat question. Half-life could be for mass as well. Yeah, it could be for mass. It's also a term in, pharmacology. So different drugs have a different half-life. So like the half-life of caffeine, unfortunately it's quite long. It's like 4 hours or something. So if you have a coffee at like noon, a quarter of it is still there at 8 o'clock. And you guys are students, so let me just rephrase that. If you guys have a coffee at 8 p.m., a quarter of it is still there at 4 a.m., right? So having a coffee at 8 p.m. is equivalent to having a quarter cup of coffee. Sorry, my phone is ringing. So having a coffee at 8 p.m. is equivalent to having a quarter cup of coffee at 4 a.m. And obviously you wouldn't want to have a quarter cup of coffee at 4 a.m. Or maybe, I don't know, maybe you're an early riser. Maybe you would want to. But yeah, so half-life, it's this, it's a common, it's just like a standard measurement of a decay, of an exponential decay. All right. So when time is equal to RC, your voltage has decayed down to 37% of its initial value. Right? And it's commonly written, we commonly replace RC with a tau. Right? So the time constant of an RC circuit is equal to the product of the resistance and the capacitance. And so normally you want to ask, how long does it take for your capacitor to be fully discharged? So what does that mean, fully discharged? Well, let's just assume that if it has a voltage of less than 1% of its initial value, then we'll just say that it's discharged. And so 1% is achieved after about 5 time constants. So if you actually do the math, if you set VT over V naught to 0.01, and then solve and set it to, and then solve for T, what you'll get is that T is approximately equal to 5 tau. And so we normally say that the capacitor voltage is fully discharged after 5 time constants. And so every tau seconds, your voltage gets reduced to 37% of the previous value, right? So it's like, it's, what's the word? It's compounding. So it's 37.8%. And then in tau seconds, it's 37% of the previous value. Then advance forward another tau, it's 37% of the previous value, right? So it's compounding. It's exponentially decreasing. Okay, so the smaller the time constant, the more rapid the decrease. So this is like a question that often shows up in the multiple choice part of the final. Is it will say like, circuit 1 has a time constant of ½ second, circuit 2 has a time constant of 1 second. You know, which one has a faster decay or something like that. So here's a useful picture, right? So here's a decay of an RC circuit with a time constant of 1/2, 1, and 2. So the bigger the time constant, the slower the decay. Okay, so in electronics, time constants are usually very short. They're usually below a second. Sometimes just like, you know, tens of milliseconds. This is 500 milliseconds. So again, if your time constant is large, that's a slow response. So you don't understand? Do you want to try to clarify what it is?
Yeah, I don't understand how, like, I understand how to calculate the time constant. I just don't understand what like a high or low constant means for a circuit.
Yeah, so let's make it really easy. I'm going to give you an example. So let's just assume, see, it won't let me annotate when I'm in presenter mode. Let me just see. Let's just assume some basic things. Let's assume that V naught is 1. And let's say that tau is equal to 1. Then your VT is going to be equal to e to the negative t, right? And the curve of that is basically this. And now let's take a a smaller, let's say the tau is equal to 0.1, then V of t is going to be equal to e to the power of negative 10t. And so now the argument of the exponent is going to be multiplied by 10. So this is a negative exponent. So this thing is going to go down faster. And so that's like the math behind it. But again, I think mathematically, but I know that not everyone does. Basically, in terms of the circuit, what you're going to have is, okay. I think maybe the problem is, let me just sort of draw what the circuit looks like. So the circuit is a capacitor, a resistor, and I think what confuses a lot of people is this source-free notion. You have a voltage. This is time is less than 0. And then at time greater than or equal to 0, you just have, you remove the battery, and you just have this. And so V of t is across the capacitor. It's this voltage. And this is big V here. Let's call this V naught. And the point is that before time 0, your capacitor is in parallel with the battery, so it has a value of V naught. But once you cut this battery, so once you disconnect it, all of a sudden, this voltage starts sharply declining down to 0. And the time constant tells you how fast this capacitor goes from an initial value of V naught down to 0. So at time equals to infinity, you basically have your capacitor is now just an open circuit. And it's just a dead circuit. And so, yeah, those are the 3 stages. Stage 1 is when it's charged up. Stage 2 is the important one. That's when it's going from V naught down to 0. And then stage 3 is when it's already down to 0. It's fully discharged and you're left with nothing. And so the time constant, just a measure of how fast the voltage across the capacitor goes from some initial value down to 0. And hopefully that helps. Okay. Let me see, there's other questions before I move on. Would you want the time constant to be high or low in real life circuits? Well, it depends. So actually, you want it basically to be, it depends on what frequency of input you're working with. And so if you're basically the time constant is usually tuned to a particular frequency of oscillation. So if your sinusoid has a period of 100 milliseconds, let's say, then you would want your time constant to match that. So it's not really that there's a preferable, there's a preferred value of the time constant. For now, it's enough just to understand that, and here's the key thing, the value of the resistor and the capacitor determines the time constant. So if you increase the resistance, you increase the time constant. And so you control the time constant. If you reduce the resistance, you shorten the time constant. And so it's the circuit components that determine how fast, what the transient response is of your RC circuit. All right, let's continue on. All right, so now that we have, so remember V of t is an expression for the voltage across the capacitor. And we also know from, let's see, from the original picture, right? V of t is the voltage across the capacitor and the resistor. And we are interested in solving for the current through the resistor. And so fast forward to where we were. The current through the resistor is equal to the voltage V, which is shared by the resistor and the capacitor, divided by the resistance. In other words, V naught e to the power of negative t over tau divided by R. And then if you want it could be power dissipated in the resistor, you would just multiply this by V. So basically the only difference is that you have to square everything except for the resistance value, right? Because V of t is equal to V naught times e to the minus t over tau. So your power dissipation is proportional to the square of the initial voltage. And notice that the power falls off at twice as fast, basically, as the voltage. Energy is just the integral of power. Sorry. And so the integral of this, right, the V naught squared over R is a constant, so it can be moved to the front. And I'm going to spare you of the mathematical details here. I trust that you all know how to integrate an exponential. The important thing here is the final form of the solution. Namely that when time goes to infinity, the energy stored in the resistor is equal to 1/2 CV naught squared, which is interesting because that was the initial energy stored in the capacitor. So at time equals to infinity, all of the energy that was in the capacitor has been transferred over to the resistor, right? And so that's essentially what happens in an RC circuit, is that the energy that's stored in the electric field of the capacitor gets transferred over to the resistor. All right. We're in desperate need of an example, and we're going to have one on the next slide, but just to wrap up this theoretical component, basically you're looking for two quantities. The initial voltage V naught, which is often given to you, or if it's not given to you, then you have the tools to solve for it. And the second thing is the time constant tau. Right. So another way of viewing, one way of viewing the R in time constant is that it's the Thevenin resistance when looking from the vantage point of the capacitor. So in other words, if we take out the capacitor and you measure how much resistance it sees, that's the value of R in R times C. And this is important when you get to circuits that have more than one resistor. Then you have to do some combining of resistances. And this will all become clearer, I hope, in some of the following examples. All right. Our first RC circuit. We have I'm sorry, I don't know why I'm yawning so much today. I don't know what the evolutionary basis for yawning is, but I'm not particularly that tired. Maybe it's just the first order circuits. So we're told in this circuit that the initial value of the capacitor is 15 volts. And we are asked to find VC, Vx, and Ix for all time after 0. Okay, so here's an example where you have an RC circuit, but you need to combine the resistors, right? So the first thing that we should do is look from the vantage point of the capacitor and find out how much resistance it sees. So if you're looking from the capacitor, what is the equivalent resistance as seen from these two terminals?
Four ohms.
Excellent. That's outstanding. And how did you get the 4?
Well, it goes up and then it splits off into 2 branches. And I combined the 8 and 12 to 20 and the other one to 5, and they're in parallel to each other.
Exactly.
The result is just 4.
That's right. That's awesome. That's exactly right. So the 8 and the 12 are in series, so they can be combined to a 20. And that 20 is in parallel with the 5. And so product divided by sum is equal to 4 ohms. Okay, so that's our equivalent resistance. And so right away, we know that our time constant is going to be equal to 4 ohms times 0.1 farads. Right, so it's going to be equal to 0.4 seconds. Okay, so this circuit can be effectively redrawn as this circuit where REQ is equal to 4. Let's see. So now we have everything. We have for VC, we have everything, right? We know that the initial value of VC was given to us as 15, and its time constant is 0.4. And so so we plug in 15 for V naught, and we plug in 0.4 for tau. And so our capacitor voltage is equal to 15 times e to the negative 2.5 t volts. All right. Let's move on. We still have to find V of x and I of x. And so, right, so I'm just gonna tell you this one because I think this one confuses a lot of people. How do you go from VC to VX? Notice that you can think of VC as a battery that connects this node to this node. And that VC gets put across 2 resistors in series, an 8 ohm and a 12 ohm. And so you can use voltage division to determine the value of Vx starting from VC. And so Vx is equal to VC times 12 over 12 plus 8. So in other words, it's this value multiplied by 12 divided by 20. So 60% of 15 is 9. So again, you can think of this, if that's not clear, the way to visualize this is if you have, let's see, you have a battery. It's VC. That's connected to the 8 ohm. And the 12 ohm. Right? And this is Vx. Go ahead. Ask your question.
We don't have to worry about the 5 ohm because the same voltage goes across both branches, right?
Yeah, exactly. So the 5 ohm is sitting at VC, right? So everything's in parallel. And so Vx is equal to VC times 12 over 12 plus 8, which gives you this. And then Ix is just Vx divided by 12, right? Because this is just the application of Ohm's law. And so the key thing in this question is to first solve for V of C, and then use voltage division to go from V of C to V of X. And then divide V of X by 12 to get I of X. Okay. Is there any questions on that problem? Alrighty, we will move on. To our practice problem, which I would normally solve on the board. I don't have that luxury here. All right. So this one's not too different from the previous one. Right. So we're given that the initial value of the capacitor voltage is 30 volts. And we are asked to find VC, Vx, and I naught, all for time greater than or equal to 0. So at time 0, this capacitor is sitting at 30 volts. So let's figure out the time constant first. So we know to get the time constant, we need to figure out the R. We know the value of the C. The C is equal to 1/3 farads. Oops. So what's the value? How much resistance does this capacitor C in this network? Right, so it sees the 8 ohms, that's in series, plus the parallel combination of 12 and 6. So 12 and 6 in parallel combine to 4, and those add to 8 to give you 12 ohms total. All right, so our equivalent resistance in this RC circuit is equal to 12 ohms, which means that our RC constant is equal to 12 times 1/3. Right? And so that's equal to 4. So there should be more detail. This is equal to 4, and therefore V naught is equal to 30 times e to the negative quarter. And just because I realized that this was a bit, oh, we have a question. R equals 12. Sorry, I don't see my chats at all when I'm in the presenter view. I'm going to change this, or maybe that's going to bring back this awful problem, but I'm going to disconnect my external monitor. Okay. So remember that our fundamental equation is VC. Oh, my writing is awful. V naught times e negative t over RC, right? So the value of RC is equal to 4. That's equal to 4. And the value of V naught is 30. Oh, let me answer the chats. Oh, I love it when the students answer the question. That's awesome. Yeah. So as was answered, it's just The 6 and the 12 are in parallel, and 6 times 12 divided by 6 plus 12 is equal to 72 over 18, which is 4, plus 8 is 12. All right. So okay. So now we know this is the expression for VC. And I want to take that and convert it into Vx. So once again, I'm going to use voltage division. But importantly, I'm going to use a resistance of 4 here. Right? So in the denominator, we have a 4. And in the numerator, we have a 4. And in the denominator, we have 4 plus 8. Because these two, the Vx applies to both the 12 and the 6 ohm. Okay, so basically, Vx is going to be equal to 1/3 of Vc. Right, so Vx is equal to V naught times 4 over 4 plus 8. Once again, you can imagine this as being a battery, and the voltage of that battery is dissipated across the 8 ohm resistor and the combination of the 12 ohm and the 6 ohm. And so that gives us a solution for Vx of 10 times e to the minus t over 4. And finally, this is actually a good test. So I have the value of V naught, of Vc, and I have the value of Vx. How do I get the value of I naught? Let's see, I have a chat answer here. Yeah, I'll explain the voltage division again. So imagine that Vc is a battery. Okay. And it gets put across and so basically what we do is we simplify this into a simple circuit where a simpler circuit where this resistor now replaces these two because these two are in parallel. So this is now 4, and this is 8, and this is Vc. So Christian, hold on a second. Just undo. I'm going to get to your answer here. Just want to finish. Just want to finish with this. So this is Vx. So Vx is equal to Vc times 4 over 4 plus 8. So that's the voltage division. And so, yeah, Christian, your answer is basically it. So the voltage across the 8 ohm resistor is going to be Vx minus Vc. And that gets divided by the 8. So I'll just annotate. So this point here is Vx. This point here is Vc. And so the voltage across the 8 ohm resistor is equal to Vx minus Vc, which means that I naught is equal to 10. So it's basically this. minus this divided by 8. So it's going to be 10 minus 30, so negative 20 over 8, which is, I think, negative 2.5 times e to the negative t over 4. Okay, let me just clear these. All right. So it's I naught is equal to this voltage minus this voltage divided by 8. And it was very close to what you said, Christian. It's just that it's minus 20, and then you have to divide it by the resistance to get the current. But that was excellent. All right. Is there any questions on this problem? I think I'm going to do one more example. Yeah, so yeah, exactly. KVL is right. Okay, go ahead, Daniel. Do you have a specific thing you're confused about?
I just I get confused after you do the 6 and the 12 ohm resistor, you add them. After that, I get confused. What's the next step?
Right. So basically, the 6 and the 12 can be combined into a single resistor, correct?
Yes.
Yeah. So you basically, what your circuit has is a capacitor in series with a resistor, and then in series with another resistor. So this capacitor sees a total resistance of 8 plus 4, which is 12 ohms. So essentially, this circuit is the same as, sorry, going the wrong way here. This circuit, the one that we're working on, is identical to this circuit, where the value of R is equal to 12 ohms and the value of C is equal to whatever our capacitance is. So they're the same thing. We're just trying to get it to that canonical form. Okay, so we did this. Okay, so essentially you're trying to reduce the circuit into a capacitor in series with a resistor. And then you know that your capacitor voltage takes this form, V naught, which is given to you by 30. And then you need the time. So the time constant is equal to the product of the resistance that the capacitor sees times its own capacitance. So we just saw that this capacitor sees a total of 8 plus 4 ohms of resistance. In other words, this capacitor sees 12 ohms of resistance. That 12 ohms is multiplied by 1/3 farads to give it a time constant. So the thing that's missing here is that I should have written down is that tau is equal to R times C is equal to 12 times 1/3 is equal to 4 seconds. And then V naught is given to us as 30. Therefore, V of t is equal to 30 times exponential negative t over 4. So we're just solving for the time. In all these questions, what we're really doing is we are solving for the time constant. And you solve for the time constant by getting the equivalent resistance as seen by the capacitor. Okay. I've lost my cursor. Sorry, give me a second. How do I do this again? No, still no. Come on. Close this. There we go. Clear all. Okay. And then once we have V of C, right? This is actually a typo. I'm sorry. This should say V of C. It's because I usually solve these on the board. And then, right, so V of C is equal to 30 times exponential of negative t over 4. And once we have an expression for V of C, we use voltage division to take that voltage and split it between a voltage drop across the 8 ohm and a voltage drop across the combination of these two resistors. And because these two resistors are in series, are in parallel, Vx applies to both of them. And that is why we can use the simplified value of 4 ohms in the voltage division computation.
Okay, makes sense. Thank you.
Okay, you're welcome. Okay, let's do one more example and then I'll set you free. The switch in the circuit has been closed for a very long time and it is open at t equals to 0. Find V of t for time is greater than equal to 0. Calculate the initial energy stored in the capacitor. And so I'm going to walk you through this. The important thing to note is that what does this notation mean? So this notation means that this switch goes from closed to open at time equals 0. So before time equals 0, this switch was closed. And so what we want to do here is to redraw this circuit right before the switch went from the closed position to the open position. Okay. So for time equals 0, for time is less than 0, sorry, this switch is closed, and then our capacitor is open circuited. Why? Because a capacitor is an open circuit in DC conditions. And DC conditions is what we had at time is less than 0. Hopefully that makes sense. Okay, so this is what the circuit looks like before time 0. And so you can see that this resistor is dead. So the only thing we care about is what is the voltage across the 9 ohm resistor. So let's apply voltage division to the 9 ohm resistor. When you do that, you get that the voltage across the 9 ohm, which is equal to VC at time 0, is equal to 20 volts times 9 over 9 plus 3. In other words, the initial value of the capacitor voltage is equal to 15 volts. Okay, moving on. And so since basically, since we know that a capacitor cannot have abrupt changes in voltage, we essentially use continuity and we say that the voltage at time equals, at this notation means 0 minus epsilon. So like the sliver of time right before time 0. And so because of the continuity of the capacitor voltage, we know that our initial, so the voltage of the capacitor at time 0 is given by 15 volts. So that's step 1, is to get the initial value. And then step 2 is to determine what is the time constant. And so once that switch goes to the open position, right, effectively this part of the circuit is removed. And all we have is the capacitor, the 1 ohm, and the 9 ohm resistor. And so this capacitor only sees the series combination of the 1 ohm and the 9 ohm resistors. In other words, it sees a total of 10 ohms of resistance. Right? So the REQ here is equal to 10 ohms, which means that the time constant is equal to 20 millifarads times 10 ohms. In other words, is equal to 200 milliseconds. Yes, exactly. Tau is 200 milliseconds. Right, so now we have everything. We have the initial value, which is 15 volts, and we have the time constant, which is 0.2 seconds. So we just plug it into our canonical equation, and we get that V of t is equal to 15 times e to the negative t over 0.2, which is equal to 15 times e to the negative 5t. So the big difference between this question and the previous one is that here, sorry, I'm trying to move. In this problem, and then the initial, I'm just going to gloss over this part. The initial energy is just the original energy, the initial voltage squared times 1/2 C. Okay, I'm sure you're comfortable with substituting in numbers into the two equations. What I really want to emphasize here is the big difference between what we did in this problem and the previous problems is that we had to solve for the initial capacitor voltage. And so the general strategy, and that we'll go back to over and over again in all of lecture 7 and 8, is that we're going to solve for the circuit before time 0. We're going to assume continuity at time 0. And so whatever the value was right before that switch went from the closed position to the open position, we're going to assume that it stays at that value at time 0. And once we have that, all we needed to do was to determine the time constant. All right. I want you guys to focus on your midterm preparation. The midterm is on Monday. Just say a few words. Remember what I said. You're going to have one question on nodal analysis that will involve a supernode. You'll have one question on mesh analysis that will involve a super mesh. You will have one question that will be either Thevenin or Norton analysis. So you'll have a circuit, and it will probably have a dependent source in it. And you're going to have to solve for REQ and VTH or IN and RN. The fourth problem will either be an op-amp question. You want the video from the last lecture? I prefer for that video not to go up, but I can put it up if you want. I may have to edit it. Yeah, I'll post it with some editing. I have to touch up my blemishes. Okay, I'm glad to hear that. I'm glad to hear that it was useful. Definitely the most fun I've had teaching in a long time. So the last question will either be, I wish, man, I wish. You see, I can get away with that for like a Kahoot lecture. If I put general knowledge trivia on a midterm exam, I'd get roasted. As my younger daughter likes to say, he's gonna get roasted. I can't do that on a midterm. I do actually care about you guys learning circuits. But what I may do is give you you pick your 3 out of 4. I've done that in the past. And I feel like, you guys are at such a disadvantage by doing this course, by doing all your courses remotely, that I do feel some sense of trying to equalize the questions. I don't think that, you don't have the benefits of being in a classroom, talking amongst yourselves, witnessing how awesome my lectures are in a live setting. And so I don't want to penalize you for that. And so I am going to give you a 3 out of 4. So for the 4 problems, I'll let you pick 3 of the ones that you want to do, which means that you don't have to solve all 4, but you do have to tell me which 4. Don't be one of those people that solves all 4 and then makes me figure out which one they want to ignore. Perhaps. I don't know about that. I don't know how many of you have even seen Monty Python. Oh, at least another one. All right. So nodal analysis, mesh analysis, Thevenin and Norton. And the 4th question will be either op-amp or another Thevenin and Norton question. There will be some multiple choice that you will thank me for because those will be easy. You only need to bring your brain, pieces of paper, and something to write with. Oh, and a camera. You got something to take a phone, something to take a photo with, and then upload. No. Or Norton. You won't have both. It will be Thevenin or Norton. And 4 will be Thevenin or Norton. Or op-amp. So last year I used something called Easy Quiz Design or something, Easy Exam Creator. It was kind of it worked. So you will have to upload. There will be like a portal, a website, I guess, that you'll have to. So the way it's going to work is you're going to log on to Zoom, and you will get a link. That's how my exams end up on Course Hero, or maybe they're not. I don't know. You usually get your midterms back though. So yeah, you get your midterms back usually, or at least you would have if you were in person. But if someone requests their midterm, I'll give it to them. So you're gonna log on to Zoom. You're gonna turn on your webcams, and I'll send you a link to log on to, and then you will get the questions on your computer or your tablet, or maybe your phone, although I don't recommend doing it over your phone. And then you will write down your solutions on a piece of paper. You will take a photo and you'll upload it. Great success. Is there any other questions leading into Monday?
Professor,
Yes, yeah.
Are the 4 questions difficulty same as the homework or easier than the homework?
I always get this question. So what I'll say is, that's a difficult question to answer, because what I'll say is it won't be as much work, right? I'm not going to ask you to, you're not likely to see a question that has 5 or 6 meshes in it, just because that will take you a lot of time. So I'm not going for amount of time, but I am looking to test your knowledge, right? So what I love questions that require you to think, but don't require a lot of mathematical manipulation. So I don't like a lot of, I don't like you to do pages and pages worth of math, but I do like to make you think. And so I like questions that are kind of, it's like if you see it, then it will be easy. But if you don't see it, then, you're gonna have to do some thinking. But I don't like questions that it won't be as tedious as the homeworks. I'll say that. So maybe I'll use Blackboard. Does Blackboard have an exam feature?
Yeah, it does.
It does? Is it decent?
I mean,
it's not buggy, is it?
It depends on how you set it up. So
Okay.
I had professors who didn't know how to set it up and it didn't work out for them. And I had professors who know how to set it up and it worked out perfectly for them.
Okay. So what I'll probably do is I'll test it out. Okay. Yeah, I'll have to test it out. All righty. So we will meet here on Monday at 2. Yeah, that's what I want you to do. I want you to take pics of your work and submit in the question. Now, the multiple choice questions, though, they'll just, if Blackboard accepts multiple choice, like if Blackboard has the feature functionality,
add the feature.
it does. Okay, that's what I'll do. That way, I don't have to grade all the multiple choice at least. Yeah, so we'll use Blackboard then because I don't have to pay. I had to pay for service last year, and I don't want to do it. So I'll use Blackboard. I'll set it up, and what we'll do is you have a lot of time. I'm gonna give you until 4:45, and you're not, the multiple choice will take you 10 minutes, 12, I don't know, maybe 15 minutes. And so you'll have like 2 hours plus to do 3 problems. So you really will have the time, all the time that you need. So log on to Zoom on Monday. Make sure your camera's working. And get a good night's rest. And I will see you here on Monday. I wish you guys all a nice weekend.